Some examples of pentavalent atoms are phosphorus, supposed to be an S, arsenic, and antimony. Now, if I add these few of these pentavalent atoms to my crystal lattice structure that's defined by silicon atoms forcing everything to make 4 and only 4 bonds, there's going to be an extra valence electron left over from these pentavalent atoms. They're going to bond with 4 silicon atoms and produce a material that we call N-type semiconductor. Now, if you think about a block of N-type material, it's a crystal lattice structure made of silicon with a few impurities doped into it. So one of these 3 elements, or possibly some others, as long as it has 5 valence electrons, they're forced by the structure to bond with 4 of their neighboring atoms, and only 4, so that leaves over extra electrons. Those are what we call the majority charge carriers. And those majority charge carriers, of course, in this case, are negatively charged electrons. And that's where the N comes from for the N-type, negative. And since I do have some free charge carriers and free electrons in this material, I can use it. It is a conductor. Now, we can do the same thing in the other direction. We use pentavalent atoms. We can also use trivalent atoms. So of course, tri means 3. And it works the same way as with the 5 valence electrons, except backwards, because now it's going to be forced to bond with 4 of its neighbors, but it only has 3 atoms to share, or 3 electrons rather, to share. So it's going to leave a hole where an extra electron should be. Excuse me. Now these holes also act as charge carriers. They really, a hole really doesn't exist. A hole is a hole, but electrons will jump from hole to hole if voltage is applied, and it gives the effect that the hole is moving through, and it gives the hole acts like a positively charged particle. So what we end up with now, N was for negative when we had N-type material. Here the majority carrier is the hole, and it acts as a positively charged particle. So that's like I've got some materials. Again, it's my silicon base, my silicon crystal lattice to start with. doped with these impurity atoms that had only 3 electrons, and that gives us what we call p-type semiconductor. And some examples of atoms with 3 valence electrons are boron, gallium, indium, and aluminum. It's supposed to say aluminum. And that gives us the p-type material. Now, both p-type and n-type material are not really special by themselves. They're just simply a conductor. What makes it interesting is when I combine them together and form a p-n junction. Let this be my p-type material. Here's my junction. And this be my n-type material. Remember that my p-type material has positively charged holes as their majority carriers. And my n-type material has negatively charged electrons. Now, when I put the 2 pieces of material together, the electrons right beside the junction jump over and fill in the holes. It's what we call recombination. And what happens is they cancel each other out. And they form a region on either side of the junction. This is my junction here. That's there. They form a region here on either side of that junction that is depleted of charge carriers. Guess what we call that? The depletion region. And because, before I put the 2 regions together, each one was neutrally charged. There were as many protons in the N region as there were electrons. There were as many protons in the P region as there were electrons. So when I put the 2 regions together and the electrons move over and fill in the holes, that leaves a voltage develop across that junction or across that depletion region, plus to minus that way. I believe that's right. Let me think for a second here. There was a hole here. And that turns out to be approximately 7/10 of a volt. Can't get to draw me a point here. 0.7 volts. That is not an exact figure, and it will change from diode to diode. I think the video I had you to watch may have said 6.5 or 0.65 or point whatever. But I've seen books say 0.75, 0.8, 0.65, 0.6. 0.7 seems to be about the average of all of them that all of them use, and different diodes have different voltages. So I always, the way I was taught was 0.7, so that's what I always use in my classes. It's easier to deal with than 0.65 or 0.75 when you do the math. So we'll call that 7/10 of a volt. Now let's apply a voltage to that PN junction. Let's start with a negative voltage on the left and positive on the right. There's my depletion region, and I've got my positives. This is my P region. This is my N region, and this is my depletion region. So this is positive charged holes and negatively charged electrons. So if I apply a plus charge here and a negative charge there, that's the way the battery's showing. The positive charge here is going to attract the electrons to the right and repel the positive charge holes, while the negative charge on this side is going to attract the positively charged holes to the left and repel the negatively charged electrons to the right. It's going to have the effect of making this depletion region get wider. Now the depletion region is void of charge carriers, so it's actually an insulator. And as long as I've got that insulator there, there's not going to be zero current flow. Now in real life, there can be a small leakage current in this situation. This is what we call reverse bias. And in reverse bias, ideally there's zero current, but in real life there can be a few microamps, maybe something small, of reverse leakage current, they call it. So that's what we call reverse bias. Now let's look at the opposite. Let's take my same PN junction with its depletion region. I've got P, I've got N, and I've got my plus charges over here. Minus charges over there. This time we're going to reverse the battery. So now I have a negative charge on that side and a positive charge on that side from the battery. Now what that's going to do, the negative charge from the battery is going to repel the negative electrons and push them into the depletion region. And it's also going to attract the positive holes in the P region and pull them into the depletion region, while the plus charge has the same effect. It's going to push or repel the positive holes into the depletion region, and then it's also going to attract the negatively charged electrons. So what happens is, if you have enough voltage here on the supply, you'll actually collapse the depletion region and start to have a current flow. Guess how much voltage it takes to collapse that depletion region? The 7 volts of potential that's developed across it. Now the PN junction, as we've shown it here, is essentially a diode. This is the most common diode symbol. And it has two connections. Then one side's called the anode, the P side. And the inside is called the cathode. And you'll see the anode on schematics. Sometimes they'll label it with an A. Sometimes they use a C for cathode. Sometimes they use a K. More often than not, I think I see them use a K. Sometimes you'll see the diode colored in. Sometimes you'll see it open like I had it before I started coloring it. So, and there are other types of diodes. This is the most generic kind. Let's go to the next page. This is the most generic type of diode. It's called a rectifier. Rectifier is a fancy word, and what it basically means is a method to change AC into DC. Now, the diode doesn't do it by itself, but it gets the process started. If I take AC and feed it into a diode, during the positive half cycle, I'm going to be forward biased. So I'll have a current flow, and basically the top half of my AC waveform gets passed through. But during the negative half cycle, it gets reverse biased, so I get nothing out. So if I have a series of sine waves, it's going to keep repeating that. That's what we call a half wave rectifier. And we will deal with that more in a lot more detail in another lesson. I just wanted to mention that now because that is what the name rectifier really means. We'll see that there's a way we can make a configuration of diodes, not just one, and actually fill in those gaps, flip the negative half cycle upside down. That's what we call a full wave rectifier. We'll get into that later. A different lesson later, not today, later. There are numerous different types of diodes besides the basic rectifier diode. One in particular that you see every day is the LED, which stands for light emitting diode. It's configured in such a way that as you forward bias it and run current through it, it gives off photons of light, and you can get them in different colors. Probably on your computer somewhere there's a blue light or a yellow light or a red light on right now, or maybe on the front of your television. If you have a TV remote, it's probably using an infrared diode, or possibly uses a radio signal, but it can use an infrared diode as well. So there are different options there. But again, that's something we'll deal with in a later lesson. So let's get back to, well, let me just do a quick, here's the schematic symbol for LED while I'm on the subject. Just have beams of light coming out the side of it. But again, we'll deal with some of these specialty types of diodes in a later lesson. There's actually three regions of operation that a diode can have. We already mentioned forward bias and reverse bias. Like maybe I didn't mention forward bias, but when I do have the current flow, last time I reversed the polarity of the supply so that we close the depletion region, that's what we call forward bias. So if we plot what we call the IV characteristic, that's current voltage characteristic of a diode, and that's a fancy way of saying I just want to plot current versus applied voltage. Now here's my 7/10 of a volt. I have a problem making a big enough dot to see on this thing, but we'll figure it out. So there's my 7/10 of a volt. So if I have less than 7/10 of a volt, or if my voltage is reversed, I'm going to have basically zero current. And then right about the time I hit that 7/10 of a volt, it will take off. It really should be a steeper curve than that. It's pretty well going to lock in at 7/10 of a volt. This is what we call forward bias. This is what we call reverse. Now, if we go far enough in the reverse direction, there is a point, and it's different for different diodes, where it'll start to conduct in the reverse direction. We call that saturation. Now, generally with rectifier diodes, we want to avoid saturation. We want diodes that are big enough or have a big enough saturation voltage or can go far enough in reverse without going into saturation that we'll never get there. If we're dealing with AC, if I'm dealing with an AC voltage, my regular 120 volts RMS, that has a peak voltage of 170. So this would be a plus 170, and then that'd be a minus 170. So if I've got a diode in that circuit, I don't want my 170 volts. This is peak voltage now. That's 120 volts RMS, but 170 peak. I want my saturation voltage to be bigger than 170 volts, so we don't ever get there. So I would typically choose a diode that has maybe 200 volts saturation voltage. Now there is another type of specialty diode that we call a Zener diode. Where we actually use that saturation. Its schematic symbol looks like this, where it has the letter Z built into the crossbar there. We will deal with those again in a later lesson, but this is the Zener diode we use to lock in voltages. We can get Zener diodes that have practically any saturation voltage you want, from 0.1 volt to hundreds of volts. And they're used to really clamp the voltage down at a particular value. When it goes into saturation, it holds that voltage at that saturation value. But again, let's deal with the basic diodes first. We'll get to that one later. This is a portion of a data sheet for the 1N 4001 family, or 4000 family. It starts with 4001, goes up through 4007. And if you can see, here are the maximum repeated to peak reverse voltage. This is basically your saturation voltage. So the 1N 4001 has 50 volts, 4002 has 100 volts. If I'm doing a 120 volt RMS, 170 volt peak rectifier circuit, I'm probably going to choose the 4003, because the higher you make that voltage, the more expensive the diode is. Most of your, well, I won't say most anymore, but at one time, most of your diode part numbers started with a 1N, like the ones in this example. Transistors, by the way, start with 2N. But over the years, more and more different companies have developed more and more different diodes and transistors, and they've somewhat gotten away from that, but you will still see it quite a bit. Let's see. All right, let's look at a diode circuit. The diode determines whether or not a current flows. The resistor, you still have to have a resistor there because the diode don't have any, or has very little resistance to it. When it forward biases, it's almost like a short circuit. It's like maybe a quarter of an ohm or something. So if you apply a voltage to that diode and forward bias it, there's not a resistor in the circuit, you're probably going to burn the diode up very quickly. It'll forward bias and start conducting and can't handle the amount of current. So we do need a resistor in a circuit. Now, how would I find the voltages and currents in this circuit? Well, very much the same way if the diode weren't there. There's one extra step we have to do for the diode. There's 3 tests we need to do to determine if the diode is forward biased or not. It has to meet 3 conditions. First of all, well, I'm not wanting to move the thing around now. I'm wanting to draw.